Hi, everyone. I'd like to welcome you all to today's colloquium. My name is Mark Gurwell. I'm over in radio and geoastronomy, and it's my pleasure to introduce today's speaker, Richard P. Binzel. Binzel, sorry. I always say it backwards. Anyhow, he is a professor of planetary science at MIT. He received his PhD in 1986, working on the asteroid belt, collisional evolution in the asteroid belt. He's been awarded the Urey Prize by the Division for Planetary Sciences of the American Astronomical Society. He was also awarded the McVicker Faculty Fellowship for Teaching Excellence at MIT in 1994. Despite him not talking about asteroids at this talk, he is sort of an asteroid nut. He started doing asteroids very early on. Apparently, he has an asteroid named after him, Binzel, number 2873. He was also the inventor of the Torino scale for impact hazard assessment. And he's a co-I of the OSIRIS-REx mission, which he talked about at lunch. And I can testify to how nutty he is about this. I have a little tiny piece of an asteroid that I had in my office. And I found it yesterday when I was cleaning it. I just put it out on the desk. And he immediately came into my office and said, "Hey, that's an asteroid." And he took it over to the light and went, "That's Milbilili." And he's right.
And it's from Vesta.
From Vesta. There you go. But he's here to talk to you about the New Horizons mission and about Pluto, which he has also been very active for a very long time studying. And I can tell you that Pluto made sort of a big splash, and I know this because Pluto has its own stamps now. But I'm hesitant to say this, Rick, but you know, you spent 9.5 years and untold billions of miles flying, but you could have just gone to the store and gotten some Pluto putty and learned everything you need to know about the surface. But, well, that's okay. It is my pleasure to introduce Rick Binzel.
Thank you. Thank you. It's a pleasure to be here. And I find my clicker. So I put away. I want to begin just by giving a little shout out for a project that I've been doing over here with our colleagues at Harvard, Josh Grindley, Brandon Allen, and Jason Hong. And we just launched a little instrument about the size of a shoebox. There it is up on the top of the NASA OSIRIS-REx spacecraft. It's an X-ray spectrometer that is on its way to an asteroid named Bennu, and we're going to map in X-ray light the elemental surface abundance of this asteroid and help in that sample return mission. And I just wanted to say what a pleasure it's been to work with these colleagues here, and I'm really grateful. It's one of the great highlights of my career, working with such great colleagues. So with that, we'll go on to Pluto. The most important thing I can tell you about Pluto is that I'm a member of a team. Any mission like this is not any single individual. It's an entire team effort. So please understand that I'm talking to you today about the mission as a team member, and the full credit goes across the team. And I'll highlight a little bit of that as we go along. But it's really great that I now got to change the bumper sticker on my car to say that we explored Pluto. All right, so the beginning of the story for me and Pluto goes back to when I was a graduate student, and I was working on Pluto. I'll just say something about that work. But when effectively you're the only graduate student on the planet studying Pluto, that novelty gets you the chance to meet the discoverer. So I got to meet Clyde Tombaugh. I'm the guy on the right. And I got to know Clyde very well, and I treasured that friendship. Of course, we lost Clyde in 1997, but some of his ashes are actually on board the New Horizons spacecraft. So he got to go see the world that he discovered. That's pretty neat. It's pretty neat. All right, so the work I was doing back in the 1980s goes back to the discovery of the satellite of Pluto, Charon, back in 1978. And I was actually a summer intern at the U.S. Naval Observatory in Washington, D.C., in the office next door to where Charon was discovered. So I was there actually on day one. I got to look at these original plates as people were pondering what they meant. And so we saw these elongated images of Pluto that were moving around in a 6.4-day period, and the idea was that was a satellite. And then after we realized it was a satellite, we also realized that the orbit plane of Charon was going to become edge-on at some point in the near future. So this was discovered in 1978, and the prediction was sometime in the early 80s, the orbit plane would be edge-on. Just like Saturn's ring plane crossing happens twice every Saturn orbit, it's twice every Pluto orbit, which means once every 124 years, the orbit plane of Charon is edge-on. And I happened to be a graduate student, and there was someone had funding to do this. They needed someone to spend their life at the telescope looking for these things, and I spent a week a month for 4 years looking for these things. And finally, in 1985, the onset occurred because we didn't know the obliquity very well, and we got the first planetary transit of Charon transiting across the disk of Pluto. This is long before exoplanet transits became fashionable, or we even knew the words exoplanet transits. We were doing planetary transits. So the beauty of these transits, and even though Pluto is unresolvable in a telescope from the Earth, the transits of Charon across the disk of Pluto proceeded in a regular fashion, and the two bodies are synchronously locked in total synchronous rotation and revolution of the orbit. So every time Charon transited the disk of Pluto, it was the same face, the same hemisphere of Pluto. And so we used those transit light curves over many years to reconstruct a map of Pluto. And this is before Hubble Space Telescope was even launched. And so we had the first maps of Pluto back in the 1980s. And Pluto's pretty unusual, pretty strange. It's not boring at all. It has bright poles, a dark equatorial band, and we even were seeing longitudinal variations in its brightness. And so it's hard to keep a planetary body bright because micrometeorite bombardment, cosmic ray bombardment, high energy particles from the sun will darken an icy surface. And so it was kind of a mystery as to how do you get a bright, icy Pluto. And one of the ideas was if these are freshly moved around, fresh volatiles, fresh ices that get deposited, then they have to have some means of transporting themselves around. And of course, if you're moving gases and solids around, you have to have a transient state in an atmosphere. And so my MIT colleague, Jim Elliott, who pioneered this technique of stellar occultations, which is just as a planet moves around its orbit, it occasionally passes in front of a bright distant star. And there was an event that was actually found and predicted by Jessica Mink back in the early 1980s. And the prediction was good enough that one could calculate where on Earth would you take the Kuiper Airborne Observatory to be sure you were in the shadow path of Pluto as Pluto passed in front of this star. And so this was successfully observed in June of 1988. And this is the light of the star as it went behind Pluto, and instead of just dropping instantaneously as it went behind the disk of Pluto, it dropped gradually with a little kink in it. This is the star behind the disk, and then the same kink, symmetric on the other way out, and gradually rising again. So it was evidence of an atmosphere around Pluto and maybe a haze layer or some kind of interesting temperature structure giving rise to this event. And so, as I said, Jessica was responsible for the prediction. Some familiar characters here in this photo just after the flight. There's Jim Elliott on the right. Amanda Bosch is an instructor at MIT. Steve Sliven's at Wellesley College. Leslie Young I'll talk about towards the end, and Ted Dunham is, of course, at Lowell Observatory. So really spectacular discovery and really beginning to put the pieces together of what Pluto was like. The fascinating thing about Pluto and its atmosphere is on Earth we're used to the fact that we have this molecule on our planet that's abundant on our planet called water, H2O. And the temperature of the Earth is right at the triple point of water. We see water liquid, we see frozen water, and we see water vapor. And it turns out at Pluto, at that temperature range, sort of the 40 to 60 to 80 Kelvin range, and very low pressures, nitrogen, methane, and carbon monoxide, CO, are all near their triple point. So we have lots of volatile species that, in principle, could be interacting through their various phases. So this makes Pluto pretty physically interesting, a laboratory unlike anything that goes on at the Earth. And what's more, not only do we have these different species, but Pluto has this really weird orbit. It's in a high elliptical orbit. This was where Pluto was when it was discovered. Pluto is now about here. Pluto's barely concluded 1/3 of its orbit since it was discovered. And so not only does Pluto change in its heliocentric distance from about 30 AU at perihelion to about 50 AU at aphelion, Pluto also is tipped over on it. Its obliquity is tipped over. It's tipped over by about 120 degrees, which means you get seasons where one pole is facing towards the sun and one pole is facing away from the sun. So you get these very long parts of the planet get very long Arctic winters, and other parts of the planet get very long Arctic summers. And so it's a very complex set of interactions. So these occultation measurements were continuing over the decades since 1988. And even though Pluto was at perihelion in 1989 and has been getting further and further from the sun since 1989, this is that 1988 occultation, Pluto's getting further from the sun, but its pressure from other occultation events shows the pressure increasing. So what's going on? So one idea we have is that this is one of these long Arctic summers where one of the poles, it turns out the North Pole of Pluto, is now in a long period of Arctic summer. And so there you have a lot of available ices that are being sublimating into gas, building up the atmospheric pressure. So this is a pressure model done by my graduate student, Alyssa Earle, who's here. Would you wave, please, Alyssa? There's Alyssa. She'll be needing a job in a few years. And this is just looking at how the pressure might track with insolation, just looking at the basic insolation, how much sunlight is received, and how if you just track the insolation, how the insolation is correlating very well with this pressure pressure differences being seen in the stellar occultation data. So it's really great to be a graduate student and have a prediction of what's going to happen in 20 and 30 years, because maybe someone will hire you to see if you're right. So here's what we found on Pluto. We found these bright poles, the dark equatorial bands, et cetera, et cetera. We found this complicated orbit, this very odd obliquity that could be driving seasons in a very interesting way. And we had a special session at the American Geophysical Union, or AGU meeting in Baltimore in 1989. It was a special session on Pluto. There were 12 papers in the session. And we each stood up and gave our paper to the 11 other people in the room. And then we went out to dinner. And each one of us was lamenting how much we knew, but how now we're kind of stuck. And how are we going to learn more about Pluto and understand what Pluto is? And Alan Stern had the audacity to say, we need a Pluto mission. And we all said, oh, come on, come on. Well, Voyager was about to reach Neptune and said, look, we can get to the outer solar system. We're doing it with Voyager. We should get a Pluto mission. Why not now? Why not us? And we were barely still graduate students, or just out of graduate school at that point. So pretty audacious. But we started with this idea. And this is sort of, how do you build up, how do you sell a project? And whether it's a superconductor, super collider, it's W first, or who knows what. You know, you can make the argument that you start with fundamental research, in this case for Pluto and the Kuiper Belt. You have discovery surveys, you find a lot of objects, you begin to measure them, and then some of them are incredibly interesting. They have properties that you really want to understand, so you formulate your science questions and their consequences, but often you just reach a limit, and you need to do something major to make any advancements. And you can think of spacecraft exploration as that capstone. It's very expensive, and you have to talk to a lot of congressmen and a lot of people as to why you want to fly this project. But you make the case that this is the capstone, and we've reached the limit of what we can do on Earth. So this was kind of the argument we were making. You can read all about it in a recent issue of Physics Today. I don't recommend it before you go to bed. It's a horror story. We had no fewer than 5 different versions of our mission that effectively got into Phase A study, so in the current NASA lingo. We'd move along, and then we were canceled. They'd say, but come back and try again with this idea, and come back and try again, and so forth, and so on, and so on. And this is what it felt like over and over again. So we were undaunted, and we proceeded on. The version we had in 2001 was called New Horizons. And this is just our NASA bullet chart of our objectives to characterize the geology and morphology of the surfaces, map the composition for both Pluto and Charon, study the atmospheres and their near space environments. And the key that I think that definitely put us over the top was the discovery of the Kuiper Belt, realizing that Pluto was a member of an entire new zone of the solar system. So it wasn't just one object we were studying an entire class of objects. And a mission to Pluto and the Kuiper Belt came out as the #1 recommendation in the Planetary Decadal Survey. And that's what got us over the top to get the funding to fly the mission that we call New Horizons. So the spacecraft we proposed had amazing capability. This is the technology era of the Motorola flip phone when we built New Horizons. And anyway, you can see the kind of resolution that our camera system in our proposed state could even resolve where we are here today in Cambridge. And the overall instrument is this high-resolution imager called LORRI, a couple of detectors for the particle and fields environment called PEPSI and SWAP. We had a student instrument, the first student instrument. There's a dust counter built by University of Colorado. The one that Harvard and MIT is the second student instrument ever to fly. A radio science experiment, and then a pair of spectrometers in the UV and visible and near infrared, Ralph and Alice, named after the honeymooners, for people who are old enough to remember Jackie Gleason. All right, so a question that people ask, if you're flying to Pluto, how do you maintain power for your spacecraft? Because it's too far to use solar power. And in fact, it's kind of a trick question, but it was a question I was asked one time when I was in an airport security line. Anyway, that's a story over dinner. Anyway, the answer is plutonium. What else would you use to go to Pluto than plutonium? And so this thing that you see on the back of the spacecraft is our plutonium, our thermoelectric generator using the heat from the plutonium-238. It's about a half-life of about 100 years. And so we fueled it up. It actually includes Russian plutonium because Los Alamos got shut down because someone lost a disk drive behind a copy machine. If you remember that episode, it shut down the production of plutonium in the United States. And we needed plutonium to launch. And we had a launch window because we had to hit Jupiter. And anyway, spaceflight is a really nutty business. But anyway, our spacecraft at Pluto, we had 200 watts of power. So everything you see that we did was with 200 watts of power, including transmitting back from 40 AU away. All right, so this is our launch vehicle, an Atlas V. This is the fairing of the rocket, the launch. This is our spacecraft. And in the full cutaway view, the spacecraft is this little tiny piece of this large Atlas V rocket with 5 boosters, full up, the biggest thrust that's available in the NASA fleet. And so why did we make our spacecraft so small? And it's really pretty simple. In principle, it's simple if it works. Until it doesn't work. Oh, it always makes you happy. Stand by. We'll just make it happen. All right. We'll hear that magic sound. Maybe. Wait. I love it when it happens. Sorry about that. Spinning wheel of death. Okay. All right, let's try this again. Oops. So I'll give you the answer while we're waiting for it to reboot. So the rocket delivers kinetic energy. And kinetic energy is 1/2 mv squared. And so if you want a lot of velocity, you keep your mass as small as possible. And so it was all about the mass of the spacecraft. The smaller the mass of the spacecraft, the more velocity we could put into it. And we're very selfish in wanting to get to Pluto fast for two reasons. One is that hardware doesn't live forever and doesn't work perfectly forever. So thank you very much, Microsoft, for helping me prove my point. And I don't really need to join that video conference in France, so I'll just ignore that. So basically we kept the mass of our spacecraft as low as possible so that we could get there as fast as possible so that the equipment survived, and of course so that the people who were building the spacecraft and designed it and tried so long to get to the launch pad would still be alive to see it happen. So we did finally get off the launch pad in 2006. Oh, and the other thing is that we knew from the get-go it had to be a flyby because we could not carry enough mass in terms of rocket fuel to slow down and stop. If we would then fly to Pluto and then stop and go into orbit, the amount of propellant we would have to carry exceeded the launch capability of any rocket in the fleet. And so it was, even from the get-go, we knew this had to be a flyby mission. So the thing that was driving our launch date was a window with Jupiter. Basically, once every 12 years, Jupiter is in the right place to have a gravity assist on its way to Pluto. And so we had this 2006 launch date. We actually had a 1994 launch date in mind. Once upon a time, it became a 2006 launch date. And we got off on the button on our way to Jupiter, arrived at Jupiter in 13 months, so it's the fastest spacecraft ever to Jupiter. Of course, we wanted to calibrate all our instruments, and being scientists, we wanted to do as much Jupiter science as we could. And so there we were. We had a very successful drive-by or flyby of Pluto, but we got the gravity assist we needed, which without Jupiter would have taken about 2 to 3 years longer to get to Pluto. So that boost by Jupiter helped us. But nevertheless, it was a journey of 3,463 days, counting every one of them, a distance of about 32 AU, and a little over 10 to the minus 10 megaparsecs. There is really cool stuff inside of 10 to the minus 10 megaparsecs. You ought to try it sometime. All right. So one of the challenges was to know where Pluto is. Again, we've only seen 1/3 of its orbit. And there is a historic set of plates that were taken at Lowell Observatory by Carl Lampland. And we wanted to remeasure these plates to the highest precision possible to get have as much improvement in the orbit of Pluto as we could. So this is Pluto's path along the sky since discovery in 1930 up to the 1950s, the Lampland plates. These plates came here and were measured in the Harvard plate stacks, and I don't know if it's Josh Grindley's measuring machine or who put it all together, but you guys put this together, Josh, and this was very helpful in trying to refine the orbit of Pluto, just so that we could optimize our trajectory to the greatest possible. And in the end, the final orbit refinements came from New Horizons itself imaging Pluto on its inbound leg. But this got us very close all the way in. So finally, we are getting close. This is a point where we are about 2 months prior to the encounter, and we're resolving Pluto and Charon as two separate bodies. If you make a simple calculation assuming equal densities for the two bodies, Charon's about half the size of Pluto, then you calculate that the barycenter of the system is actually outside the primary. And so it's like a double star. And Pluto is a double planet or a double dwarf planet, whatever you like to call it. And anyway, this is a great freshman physics problem to see barycentric motion in its real state. It really works this way. All right, so Pluto rotates in 6.4 days, so it's a pretty slow rotator. We have a flyby mission, which means that we're only going to see one side of the planet up close and personal. And the side that was chosen is now, thanks to Hubble, which could map the entire 360 degrees of longitude, we actually found that the biggest contrast between dark and bright was on the opposite hemisphere of Charon. And this is the hemisphere that we mapped back in the 1980s with the planetary transits. But we can, so we didn't get to see that hemisphere up close, but we did get to see it basically on the final approach. And so we can ask the question, how did we do with our 1980s era map of Pluto, taking into account that the viewing geometry, the solar aspect angle or the subsolar latitude changing from 1988 to 2015. And when we do that, we have a direct comparison to what we produced in the 1980s before Hubble compared to what New Horizons saw in the Pluto encounter, or just before the Pluto encounter. And I like to say we got a B+ and maybe even an A-. All right, so here's the scene. Here's the scenario. We've been flying for 9.5 years. Pluto had just passed perihelion in 1989, and Pluto is on its way to aphelion, and we have a flyby. So basically, it's a one-shot deal. There's going to be one moment in time where we have this incredible in situ, up-close look at Pluto. And then Pluto's going to go on its merry way and do whatever Pluto is doing. And wouldn't it be great if we could tie together the assets and things that we have on the ground to this encounter at Pluto? And we put out a call to the community. Many, many people, many observers responded. Mark Gurwell included in his team with ALMA. And this is one day out of 2 of ALMA observations of the Pluto-Charon system, fantastically resolved at high signal-to-noise ratio, confirming the presence of CO, which we knew already knew was there, but with the spectacular precision there, and detecting for the first time HCN, telling us about the very complex carbon chemistry of Pluto. I'll spend more time on that in a minute. But overall, the temperatures and the abundances that are coming out of the ALMA data match very well to the New Horizons data. And that's spectacularly important because ALMA has the potential to watch Pluto for years and years and do synoptic observations of how Pluto evolves in the coming decades and how that matches to this one-time shot. So the correlation we got right now in Encounter is spectacular, and now we have a tool for looking at seeing how Pluto evolves. Even more surprising, you may have seen, is a recent result from Chandra got into the act and actually detected Pluto in X-ray light. This was a bit of surprise. We thought we might get a couple of photons and see something, but Pluto seems to be more active in X-ray light, and it seems the escaping molecules in the atmosphere are a little more interactive with the solar heliosphere than we expected. Even another spectacular event, going back to stellar occultations, was Nature provided a very nice stellar occultation event about 2 weeks before the encounter. And this was observable in the southern hemisphere. This is the path of basically Pluto's shadow going right over New Zealand. And my colleagues at MIT, Michael Person and Amanda Bosch, and somehow their picture isn't showing up, were able to make an excellent prediction of exactly where to put the Sophia Observatory. They got it so perfectly right that the star went exactly behind the center of the disk, so the light of the star was refracted equally around the planet, and you get that central flash. And it's incredibly sensitive to the temperature and pressure of your atmosphere. So it's like a home run there that we got prior to the encounter. So again, this tie point from the Earth-based data to what we measured in situ at Pluto. So here's the final approach. Again, remember Pluto is tipped over on its side by 120 degrees. So as we're coming from the direction of the Earth and the Sun, we are coming at Pluto like it's a bullseye. And so this meant we had to optimize everything to see not only Pluto and Charon, but also the total of 5 satellites that we now know in the system. And because it's a 4.5-hour light travel delay, 4.5 hours out, 4.5 hours back, 9 hours it takes for any command to go and come back. Everything on this spacecraft had to be pre-programmed. The whole choreography of having the spacecraft adjust itself for each instrument to make its measurements, and then eventually turn itself around and talk to Earth, had to be choreographed in advance. And so you can imagine that we took more than a decade to even get approval, and then finally get to the launch pad, and then 9.5 years of flight. And there was really not much we could do in those last hours waiting for that signal to come back, but basically buckle up our seatbelts and wait. And as you know, we did it. Everything worked flawlessly. There is nothing about the encounter that we have found or discovered that didn't go exactly as planned. And the one surprise wasn't a surprise. We knew it was going to be amazing, but Pluto's not amazing. Pluto is ridiculously, fantastically complex, even more than we imagined when we were saying we need to go to Pluto. It is Pluto delivered. The bottom line is Pluto itself delivered. It seemed very popular. NASA complained that when they had the Mars landing in 2012, they got so many web hits that their website got knocked offline. Well, we did it to them again. And NASA wasn't happy they got their website knocked offline, but we loved it. Anyway, not only did we do it in terms of the spectacular performance of the spacecraft at the encounter and how amazing Pluto is, and we're going to talk about that, is how most missions have a 90-day report. So you get your data and you submit your first paper in 90 days. We published our 90-day report 90 days after the encounter came out in Science. So let's go to the science. So I have to tell you that all the names on Pluto are informal. There's a process to go through approval with the IAU. And the heart on Pluto, the famous heart of Pluto, is named after Clyde Tombaugh Reggio. And this ice field is Sputnik, actually Sputnik Planitia is actually the more proper name than Sputnik Planum. But that's the core, the large flat ice sheet. I'm going to use Sputnik Planum, but eventually we have to get our exact name right. So I'm going to look at, we're going to go to about 4 different areas, and I'm going to take you on a little tour and try to explain some of the things we've discovered. So the first one here is that on the edges of Sputnik Planum, Sputnik Planitia, is we see evidence of flowing nitrogen ice glaciers. Glaciers on Pluto, flowing glaciers. Now, we don't know whether they're active and what rate of flow they are. Maybe they were flowing at one point and now they're frozen, but we still see evidence of the flow lines. But in geologic time, at least, if not in the current era, there are active glaciers on Pluto. And we began to scratch our heads and we said, well, if we look at this phase diagram, if you think about what's the pressure under tens or hundreds of meters of nitrogen ice, you start coming up in the phase curve. And you can nip this part of the phase curve that has liquid nitrogen. And what we think is that at the base of this ice sheet, which is hundreds of meters thick as best we can tell, you actually have the capability of nitrogen in the liquid state, and that can enable the flow of that nitrogen, like a glacial flow. Pretty spectacular, pretty spectacular. We see things that are sticking up through the ice sheet, whether they're mountains sticking up through or icebergs. And literally, these may either be mountains sticking up or icebergs, and literally ice as in water ice. It turns out that frozen water will float in frozen nitrogen. How about that? And that at 40 degrees Kelvin, frozen water has the strength of granite. And so think of water being so cold, it's like a rock. And we even see evidence behind this feature of maybe wind streaks. So we know there's an atmosphere there, and here's maybe a telltale sign of the global circulation pattern, or something about the circulation pattern of winds on Pluto. So we're getting atmospheric data, atmospheric information by looking at the surface. And spectacularly, I don't know how well it shows up in this projection, but we see these hexagonal features on the ice sheet. And they look like convection cells in your oatmeal or on the sun. And so we were thinking from the get-go, are those convection cells? That's crazy. How can those be convection cells? Well, they are convection cells. And so basically what we did is we said, what is the heat flow like on Pluto? And in terms of, you just form it out of the basic elements of the solar system. And what's the radiogenic material that could generate heat, even 4.5 billion years after formation? And it turns out Pluto has a heat flow rate of about 2 to 3 milliwatts per square meter, or a couple 0.02, about 2% that of the Earth. And when you do a calculation of what is the temperature at the base of the ice layer versus the temperature of the surface that's pointed out to space, so you look at that delta T, you think about the depth of your ice sheet, and you calculate this, the Rayleigh number, and a lot of people are familiar with the Rayleigh number. Very high Rayleigh number tells you that convection is possible. And when we do that and we look at the underlying temperature, the basal temperature for Pluto, compared to the depth in meters of this ice sheet, we see as long as the depth of the ice sheet is more than 400 to 600 meters thick, and we think it's maybe up to 1,000 meters thick, that convection becomes possible, and that these really are convection cells on Pluto, active convection on Pluto. And one of the clues is there are no craters. Craters form all the time, and this ice sheet could be as young as yesterday or as young as 1 million years or something, but very young geologically. And so just the fact that it's not crater filled told us that some process must be resurfacing it. And it's fully consistent with this convection. The convection cells are larger towards the center, which makes sense because we believe that this is not, I don't think this is, we have a team paper that's soon to come out, we believe, that we are thinking that Sputnik Planum is really an impact basin that's filled in with nitrogen ice. And in scale to the size of Mercury, it's very much like Caloris Basin on Mercury. And this, I may have said, but the scale of the convection cells is larger at the point where we think this impact basin is deeper, just as you would expect according to the Rayleigh criterion. So glaciers on Pluto, convection on Pluto. We see mountains, mountain building, mountain processes on Pluto. We have mountains that we propose names not after presidential candidates, but after explorers of Mount Everest, Hillary and Norgay. And the mountains that we see on Pluto we think are water ice, again remembering that the strength of water at 40 Kelvin is like granite, but nitrogen and methane at these temperatures still have enough plasticity to them that they could not hold themselves up. These mountains are basically 4,000 to 5,000 meters tall. Basically think the Rockies and the Alps on Pluto, and they're all made out of water ice. So we see amazing mountain processes on Pluto. And down in this corner is a feature that we call Right Mons. Let's see, do I have a label for it? There it is. Right Mons. It's circular and has a crater at the top or a caldera at the top. It looks like a shield volcano built out of water ice. And after questions and things, anyone wants to stick around, I have this in 3D. We put on the funny glasses and we can look at this in 3D. So it seems crazy to talk about a shield ice shield volcano on Pluto, but everything we know seems to fit it. And it seems to be young because we only see one crater on the side. Spectacular. So that's got us scratching our heads, but that's the best answer or best guess we've got for what this feature is. And it looks like it's young based on the fact that it's not pummeled with craters. All right. So moving on to sort of the global scale, one of the features we saw, we knew about from way back when was this dark equatorial band, and even the fact that we see very different features all across Pluto. Some of them seem to be spaced out in latitude. So we began to think about sort of the long-term seasonal processes on Pluto, remembering the Earth's obliquity is 23 degrees. Pluto is tipped over 120 degrees. And that means that the tropics on Earth go from plus or minus 23 degrees latitude. But with Pluto so tipped over, it turns out that the tropics go almost to the poles of Pluto. And so there's Pluto's tropics. On Pluto, so this is the region on Pluto where the sun can, at some point in the orbit, be directly overhead. And then the Arctic Circle, which parts of Pluto experience either long Arctic summers or long Arctic winters. And the Arctic Circle pushes all the way down to about latitude 30 degrees. So the tropics go to 60 north, the Arctic Circle comes down to 30 north, which means the Arctic Circle is closer to the equator than the tropics. It's kind of interesting. And you even get a region on Pluto that is both tropical and Arctic, and completely unlike anything that we experience on the Earth. And so as we're trying to decode all these complicated landforms and features on Pluto, we think these very complex seasons are coming into play. And it turns out there's this one region, this one band on Pluto between plus or minus 13 degrees latitude that never is Arctic. It never experiences a long period of Arctic winter. It always has a day-night cycle, so it's the diurnal zone on Pluto, and that's the dark equatorial band. And we just think that it just never has a long period of Arctic winter to build up a big layer of frozen volatiles. And instead, there's something dark and red that's making that zone, and I'll come to that part of the story in just a minute. So this is the current Pluto in terms of its obliquity. When Pluto's at perihelion, the sun is over the equator, and this is the pressure model from Alyssa Earle that I showed you earlier. But what about the long term? What about the long term of this? Well, it turns out that if you look at Pluto's obliquity variation for about 2.8 million years, its minimum obliquity is 103 degrees. And about 0.8 million years ago, the orbit had precessed, the precession of the longitude of perihelion, was such that the sun was directly over the North Pole at perihelion. So it's tipped over, nearly pull onto the sun, and the North Pole has an extended period pointing at the sun at perihelion. And when you redo the pressure model, you see a very much higher set of pressures that become possible in the models. And you can even get to Mars-like pressures on Pluto during these super seasons. And this is a paper that Alyssa has in press. So, well, what do we see on Pluto? Well, we actually see evidence that maybe there were past super seasons on Pluto, because we see what almost look like channels of flowing, probably liquid nitrogen flow channels. This looks like it was liquid or mushy or slushy and then refroze, and even what looks like a frozen lake of nitrogen ice, so which would have had to have been liquid, followed the gravitational potential field to smooth out and then refreeze. So we may see past epochs of very different seasons on Pluto. In terms of composition, this is a very preliminary methane map, near-infrared spectral map of Pluto, but it's the most famous near-infrared spectrum in history. So why do I make that claim? Is because at the time of the encounter, it was shown at Times Square. So this spectrum was seen by millions and millions of people. All right, so now the more grown-up version of these is a paper led by Will Grundy, and looking at regions on Pluto where we map the greatest abundance of methane, the greatest abundance of nitrogen, and the greatest abundances of CO. So we're getting to the more sophisticated level of the mapping, and we're trying to see if we can tie this into the seasonal processes and how the ices might come and go and move themselves along over these long periods of time, and it's a work in progress. All right, so why is Pluto red? So here's just getting to the chemistry in a little more detail. Why is Pluto red? So it's natural. This is the natural color of Pluto. And what we think is happening is realizing that we have methane in the atmosphere of Pluto. Ultraviolet radiation from the sun breaks apart the methane molecules, and then they recombine. You have all this carbon available, carbon and hydrogen available. recombines in much more complex molecules down to the point of these things like acetylene, ethylene, ethane. And these begin to settle out of the atmosphere, and they're called tholins. This was a kind of carbon chemistry that Carl Sagan worked on back in the 1970s. And we think that these are, the red is caused by these carbon, little more complex carbon compounds forming in the atmosphere and settling down to the surface. And that just means, and it turns out that if you have these carbon compounds and you expose them to more and more ultraviolet radiation, they get darker and darker the more they get exposed. So the older regions on Pluto should be darker, and older parts of Pluto should be more heavily cratered. And in fact, this dark region we see on Pluto called Cthulhu is the darkest and has the most craters. So it is the darkest and oldest part of Pluto. So this part of the chemistry seems to be making sense. And as I said, Tombaugh Regio is crater-free. It is the least red part of the planet, and so it all makes some sense. All right, so we not only had Pluto, we also had Charon in the system. The question was, is it going to be heavily cratered or relatively uncratered for some process? I thought Charon would be heavily cratered, but I was wrong. We see Charon also being relatively crater-free, probably because after its formation, probably by a giant impact into Pluto, making the Charon and the whole satellite system like the Earth-Moon system, that it had a lot of tidal interaction that resurfaced it early in its age. And so it is not as totally cratered as it might have been from the very beginning. Charon also has this fantastic feature, this red cap on the pole. This paper just came out in Nature, where we look at the red polar cap on Charon, and this is a temperature calculation. It just says, okay, over the course of this is the current orbit of Pluto, what are the temperatures like at different latitudes on Pluto? And maybe not surprisingly, the coldest place and the longest persistently cold place on Charon, the longest consistently cold place on Charon is the pole, the North Pole, and it should be the same for the South Pole. And the idea is, as Pluto and its methane molecules in the atmosphere, some of them do escape, some of them will make it to Charon, and those molecules will preferentially last on the arrive and stick and basically reside at the coldest places on Charon, where then they get exposed to ultraviolet radiation from the sun. And we think that the red poles on Charon is trapped methane that escaped from Pluto and has just been subsequently reddened. And if that's the case, then why is it so confined to the pole? And again, going back to these long-term obliquity models, there's a region on Pluto where the sun is never overhead. The tropics end. This part of Pluto is the part that never gets the direct overhead sun, so the annual thermal wave never penetrates as deeply there, and should be the longest, coldest residence place on Pluto. And it's not a bad relative match between this, what we think should be the broadest, coldest region on Charon and where we see the red deposit. So again, these long-term cycles appear to be coming into play. All right, so it's not just Pluto that we saw, but also the full family of satellites. And I'm going to speak just briefly about Charon and Hydra. This is the currently released. We have spectra of at least Nix and maybe the others that I don't think they're released yet. But Charon and Hydra both appear to have the spectral characteristics of water ice. We knew that for Charon from long ago. But at least so far, it looks like the composition of Charon and the whole satellite system is consistent with one another and consistent with this idea of a giant impact forming the full satellite system. This is one of my favorite pictures, and you have to think about it. This is the dark side of Pluto. In principle, with a massive, amazing telescope, you could see this stuff from the Earth. But you can never get the view of the sun in total eclipse behind Pluto unless you are a traveler beyond Pluto. Really spectacular image. And it's blue. Look at the Rayleigh scattering. Blue, because it's nitrogen, just like the Rayleigh scattering nitrogen that our atmosphere does. Pluto's doing the same thing. Anyway, I love that picture. I love that picture. So we are going on, we're a flyby, we're going out into the Kuiper Belt, and we wanted to go see what else is on our path. What other object could we go to? So we began searching. Once we got off the launch pad and we knew our trajectory, we began searching. And we said, oh, great, let's just figure out where an object would be after Pluto and where would it be now that we could start observing it and our spacecraft would encounter it. And wouldn't you know, smack dab in the Milky Way is where our potential flyby targets beyond Pluto would reside. And so this was nature getting back at us, as it often likes to do. So this became an impossible task. But we took it on in earnest in beginning in 2011 because the whole region of search began to shrink into a level that was comfortable enough. So we were using the Magellan telescopes for a number of years to look for potential targets. Ultimately, we went to Hubble and we said, we're not successful from the ground. We need help. And Hubble came to the rescue. And thank you to anyone who was on the Hubble TAC who supported us in this, and we did find a target right on our path, pretty much right on our path. It's called 2014 MU69. When we found it, we just codenamed it PT1, Potential Target 1. And anyway, we are now on a trajectory towards MU69, arriving in early January 2019. So again, a flyby of this target. We think the object is about 50 kilometers across. This is the CG comet that Rosetta was examining. We think that the comets may be coming in out of the Kuiper belt. So a comet is often the case of a Kuiper belt object that comes to us. Now, for the first time, we're going to one of them. And there you see it to size. The kind of resolution that we expect to get on our flyby is illustrated here. This is Phobos, but just kind of gauging the resolution we hope to get at MU69. Based on Phobos. So this should be a really spectacular encounter of a Kuiper belt object. All right, so just a couple things in summary. As we got all this media attention at the time of the encounter, reporters started commenting. They said, I just talked to one of your key scientists or key engineers. It was a woman. And the other reporter said, I talked to somebody who was important too. It was a woman. And it turns out, and I don't know the exact number, maybe Alyssa remembers, 30 or 40%, do you remember the number? 30-ish. Anyway, 30-something% of our team, which is historic for NASA, were women. And I like to say that I don't think we were very deliberate about this. We were just hiring the best people. And anyway, we're very proud that we're the most women-represented mission ever in NASA history. And we're just getting going. You know, it's not where we want to be. But we're proud that we maybe have a little measurable progress here for New Horizons. So we'd like to talk about that. Anyway, also to talk about teachers and professors and the legacy of my colleague Jim Elliott. These are students of Jim's who have gone on to careers involving Pluto, and you'll recognize some of them. But two of them, Leslie Young and Kathy Oken, are both deputy project scientists on the New Horizons mission. So it's a great, great legacy of our colleagues, and many of you here knew Jim Elliott. We have a fellowship fund at MIT named in his honor. Some of you have donated to this. I really, really appreciate it. And if it's of any interest, I'll be happy to put you in contact with the right people. But it's a tremendous tribute to Jim, who was a great mentor and a great pioneer. All right, well, to wrap up, you might remember in 1991, there were a set of planetary stamps issued, and all the planets. And when they got to Pluto, this was the best they could come up with. And Mark already showed, Harold, thank you for having the real deal. These stamps really do exist. And it's pretty neat because normally you have to be dead to get on a postage stamp. So we at least got our mission on a postage stamp. And so we're really happy about that. All right. So in summary, I like to step back and take a big historical view of things. And it's really kind of amazing when you think 200 years ago, or just over 200 years ago, what was the frontier of exploration? At least from an American perspective, the frontier of exploration was the journey of Lewis and Clark across the continent. 200 years ago, the far frontier was just to go across the continent. And what have we seen? What have we seen? Well, we've seen humans to the moon, and we've seen our spacecraft go across the solar system. And so as a species, we have advanced from being able to go across a continent to now being able to go across the solar system in just 200 years. I think that's pretty amazing. I'm stunned and marveled by it myself. But even more importantly, I think, from the perspective of the New Horizons encounter, we hope it's something more. It got so much attention, and kids just seem to really love this. And this is the first time we have gone to a new place for the first time since Apollo. And so more than anything, as a team, we hope that New Horizons ends up being the Apollo moment for a new generation. And we'll find out in about 15 years when they start showing up at Harvard and MIT. So with that, and then just to show that we've had an impact, this is not my bedroom. This came in over the transom that some kid out there convinced mom and dad to deck out his bedroom like that. So now I know what I want. So with that, like I said at the very beginning, this is a team effort. I'm just one member of the team. And on behalf of the team, thank you very much.
All right, with that, we will open it up to questions for Rick.
Hi.
So all that N2 and CO and methane, is that thought to be primordial, and does that mean that Pluto formed beyond the nitrogen cell line, or what's that question?
So the question is a N2 CO CH4 primordial? In principle, yes, it should have formed cold enough that those did condense out in the early planetary sequence. And we see lots of those raw building blocks just in the Kuiper belt. So that's really the reason, the reason why we want to explore Pluto and even see the smaller Kuiper belt objects. Because Pluto looks like it's had a lot of geologic processing, but the smaller Kuiper belt objects should very much be native time capsules to the very earliest solar system. So yeah, so we do think it's primordial, and that's really one of the big science drivers for our extended mission, which just got approval. We do have NASA approval and funding for our extended mission, so that came out of a senior review process. And we received the highest grade possible on our extended mission. We studied hard, we passed our test. Yes?
So what's the date for the next targeted?
January 2019. It's actually January 1st, 2019. As we like to say, as you know in the business, space knows no weekends, space knows no holidays.
How much more time is there for, as far as power goes, to go beyond PT1?
Oh, that's great. Great question. So when do we run out of power? So we're on our slow decay curve of our plutonium. It depends what you do with the spacecraft, but eventually the plutonium decays and we freeze to death. All right. So it's just what you do with the power that you have, and probably in the end, if we're not allowed to think about what we want to do beyond the Kuiper belt encounter, though we're starting to have ideas. But we think we could go into the 2030s. And what do you keep on? You have to say, what do we start turning off? And then if you're just down to the radio, how long can you go? And I think we can go into the 2030s. But eventually we just freeze to death.
You haven't identified any targets then?
So there's no other known target that we see after MU69, though we are starting to think about where could we search on that. But we're going to use all the remaining fuel on board to optimize the encounter with MU69. We're not going to shortchange anything. We're going to get the best encounter we can with this object. And then maybe at that point we'll know if there's another follow-on on our path, but we're not going to sacrifice science that's in front of us for science that we might do again. We want to optimize what it is that's squarely on our plate.
Yeah, in that connection, how typical do you think Pluto is of other KBOs?
Well, some other people might help me here because I don't have all the KBO catalog in my head, but Eris, Makemake, others, there are other ones that are very high, very bright. And so they probably do have atmospheres, they probably do have some sort of seasonal processing going on. So Pluto could very well be the tip of the iceberg. I'm sure other people here can answer a little better than
Next question here.
Regarding the changing of liquidity, is that the double planet orbital axis, or is that measured from?
So both of them, so Pluto and Charon are basically tidally locked like a rigid bar between them. So both of them are precessing.
And how is that measured?
How's it measured?
From the transit?
No, we don't have a direct measurement of it. It's just looking at the torques in the system, basically Jupiter and Neptune, how they're torquing on Pluto. So it's a prediction. And it goes back into the 1980s.
So you showed a comparison of the image constructed from the transits and the real image.
Right.
And in the transit image, there was a bright spot that I saw, which seemed to have very high contrast.
Right.
And it was not seen in this other image. So do you think that was really there and something is changed?
Yeah, that's. I won't go back and show it because I don't want to over-interpret it. Yes, so there was a brighter region sort of on the right side here. It is brightish there in the New Horizons data, and it's just at the limit. Do we want to interpret it as a limitation in the mapping, or do we want to interpret it as part of a seasonal variation? So it's right on the edge, and I've resisted going there. At least at this point, we've got plenty of other things to do. But it's one on my to-do list is to go back and really think about that and say, do we have a case and an argument that here's a real seasonal change? And we can do the same with the Hubble maps that we have that go back into the 1990s.
As I recall, looking backwards towards the sun, there were many, many layers in the
Oh,
atmosphere.
yes,
I
yes.
have no idea what they are.
Yes, yes. So there was this structured layer in the atmosphere, all these haze layers, and we don't understand them very much either. We don't know if it's sort of day-night cycling of the atmosphere and these tholins. It might be these particles raining out, and we don't know whether it's on a daily basis or sort of a longer-term seasonal basis. So we see all these things on Pluto, and the thing we don't understand is the timescales. We see stuff is happening, but we don't know if it's happening on the timescale of a rotation or a Pluto orbit or one of these obliquity seasons. And so, that's that. We want to go back, right? And do we go back in a decade? Do we go back in 50 years? I don't know. Do we have any undergraduates here? Anyone have a preschooler? But almost in all seriousness, that's the kind of timescale thinking, I think, for really unraveling these processes on Pluto. It's going to take another look on the decadal timescales to see how Pluto is evolving, and maybe even a century timescale to see what's Pluto doing in aphelion compared to what it's doing now with late perihelion. So, anyway, stay tuned. I think Pluto's going to be a long, fascinating story.
What do we know about Pluto's magnetic field?
Nothing. We had no magnetometer on board, so it was one of the sacrifices you make. It's not that a magnetometer is particularly expensive, it's making a magnetically clean spacecraft that's expensive. And then you have to have it on a boom and things like that. So the magnetometer was just not in the cards. And of all the things, we had a list of science objectives that we wanted to accomplish with Pluto. And the only one that we said we could not do when we proposed was the magnetic field. No, I agree, it's a loss, but cost-constrained thing seems to be the first to go.
Yeah, was there a bow shock as you were coming in?
Yeah, so we looked for that, but very little, very little. We were surprised, actually. We thought we would be encountering more of the escaping atmosphere as we came in, and it was lower than what we predicted, which makes the whole X-ray interaction a little more puzzling, because we were saying, well, not a lot of the atmosphere is escaping, but there does seem to be all these X-ray interactions. So that's kind of like the opposite answers from Chandra. So anyway, so that's good. It gives us something to figure out.
All right. Well, I'd like to thank Rick once again
Thank you.
for coming.